The midsem exam for another professor Shankaram is fixed on March 23rd. So
Okay.
I need to get your exam date also. Based on that, some of the people are from Mumbai and Pune. It is better we can club on the same the 24th. Then the number of trial will reduce for them. That is what I want to discuss. So maybe now post to the class we will discuss.
Actually, the problem is I don't have midsem. I made it clear in the beginning that we will have quizzes, quiz 1, 2,
Yeah.
and then end exam. So you will have to take 3 exams instead of 2 exams. I think it depends on the course. He is going to conduct 2 exams, midsem and endsem. Okay. So in this particular course, you will have 3 exams, 2 quizzes and 1 end semester exam. So because of that, it's impossible to have same schedule because he is having 2 exams, right? So probably the quiz 1 exam for you will be by the last week of February.
Okay, sir.
I will give the exact date, but you can just take a note that it will be by last week of February.
Okay.
If I conduct it on March, it is impossible. I cannot have 3 exams. So by April, your course will be over, last week of April. So I have to conduct it in February, 1 exam, and maybe last week of March, another exam.
That is what I want. Second, please.
So it will be by last week of February, probably Saturday, Sunday. I will try to make it on holiday so that it's not a problem for you.
Okay. So
I am available on Sunday also. So if you want, I will also make it on Sunday. I can come on Sunday and conduct the exam. Okay. So I will see that it's not a problem for you, but having this 2 course exam on the same day is impossible because the way it is structured is different.
So what will be the tentative second quiz dates?
Last week of March. Typically 1 month difference.
Okay.
And maybe by May first week, you will have your end semester exam. So your second quiz probably is last week of March or first week of April. I will provide you the exact dates as we move on. It depends on the content that we are going to discuss. Okay, so there is a minimum content that needs to be completed before I conduct an exam.
Okay.
Fine?
Right, sir.
Okay, fine. Okay, I'll record this meeting and I'll share my screen now.
Okay.
Is my screen visible to you?
Yes, sir. Yes, sir.
Thank you. So let's start with the attendance. Please answer your attendance. Aditya Kumar?
Yes, sir.
Anand?
Yes, sir.
Anand Kumar?
Yes, sir.
Urnachalam?
Yes, sir.
Hasan?
Present, sir.
Hemant?
Yes, sir.
Jehan?
Yes, sir.
Keshav Prasad?
Yes, sir.
Lakshmi Narayanan?
Present, sir.
Prabhakaran?
Present, sir.
Prem Vinayak?
Present, sir.
Rahul?
Present, sir.
Rausan Kumar?
Present, sir.
Abhis Kumar?
Present, sir.
Satish Kumar?
Present, sir.
I'm getting some continuous feedback from you. Can you please mute the mic? I think Mr. Hasan. Can you please mute the mic? Okay, thank you.
Yeah, sorry, sir.
No problem. Titus?
Present, sir.
Pallish?
Yes, sir.
Vigneshwaran?
Present, sir.
Vijayaraj?
Present, sir.
Vikash?
Present, sir.
Vivekanand?
Present, sir.
Yadav?
Present, sir.
Yuvraj?
Present, sir.
Thank you. So those who are not talking, can you please mute your mic? Otherwise, it will be a disturbance for all. I hope I request you to do that. Be conscious about whether your mic is muted or unmuted. Okay, and just check and mute it, right? So it will help all of us. Fine. So with that note, let us get started. Okay, so good evening and welcome back to this class. So we are in chapter 1. Here, so far we discussed about the role of fuel in engine combustion. And then we discuss the criteria used to select fuel for automotive engine application. There we found that almost 99% of the fuel that we use in transport sector is from liquid phase fuel. Okay, only 1% is from gas phase fuel. In that 99%, 95% of the liquid fuel that we used in transport sector are from crude oil. Okay, so crude oil based fuels play a dominant role in meeting the transport sector demand, fuel demand. So then we discussed how this crude oil is processed to get gasoline and diesel that we use in spark ignited and compression ignited engine. Okay, after understanding that, so the purpose of looking at how these fuels are produced is to see the origin or source of this fuel in order to get information about molecular composition and molecular structure, which are important to know from the combustion perspective, as I already said. So we now understood how crude oil is processed to get gasoline and diesel. From that, we moved on and discussed about this molecular composition and molecular structure of hydrocarbon present in gasoline and diesel. So this is what we were doing in the last class. I will continue that. So what we have discussed about the composition of these two fuel, which play a dominant role in IC engine application, gasoline for SI engine and diesel for CI engine. These are complex multi-component mixture, hydrocarbon mixture. As I said, they consist of around 1,000 different hydrocarbons. The number is given in range. It depends on the source, crude oil source, which is not the same across the globe, which is going to be different. Accordingly, you have a range of hydrocarbon present in these two fuel. Nevertheless, it's a complex mixture because you have more number of hydrocarbon. Fortunately, all these different hydrocarbon can be grouped into 5 classes. This hydrocarbon, meaning that these hydrocarbons have only 5 distinct molecular structure. So these are the 5 molecular structure, 5 distinct molecular structure of hydrocarbon present in gasoline and diesel. Okay, so and after this we also have seen that depending on the molecular structure, the fundamental fuel properties are going to be significantly different. So here I discuss about how this molecular structure affects cetane number, which is a measure of ignition quality of the fuel. Based on the difference in the molecular structure, the ignition quality of the fuel defined in terms of measurable property cetane number is significantly different. For example, normal paraffin has more better ignition quality. It has a higher cetane number. Aromatics with a ring and a double bond, they have a very stable molecular structure, and because of that, they have a very poor ignition quality defined in terms of cetane number, which is 0. Okay, so which doesn't ignite. The physical inference of this ignition quality variation based on molecular structure is, depending on the molecular structure, the radical formation tendency is going to be different. So I already said that the combustion reaction is initiated by forming radical from stable molecular structure of fuel. So you are providing activation energy or thermal energy in the beginning to initiate the combustion. In SI engine, you do this by spark discharge. In CI engine, you do this by injecting or spraying fuel into high pressure, high temperature air. Compressed air pressure and temperature is what is igniting. That's why it is referred as compression ignition engine. So we provide thermal energy to form radical. Once the radicals are formed, the combustion reaction will go on its own because it's a self-sustaining process. As long as sufficient radicals are available, the combustion even continue to happen. Thermal energy is released, and we are converting that into work in our IC engine. Okay, so this molecular structure, what we understood, has a significant effect on the ignition quality, which is one of the fundamental fuel quality. Okay. So after that, we discuss this composition, okay, in terms of carbon number distribution and hydrocarbon class, these 5 classes, how they are distributed. This is for gasoline, this is for diesel. Gasoline, you primarily have a low molecular weight hydrocarbon. Carbon number varies from C3 to C13. So you have a low molecular weight hydrocarbon, meaning that they are light distillate, low boiling range. And in terms of hydrocarbon class composition, isoparaffin, olefin, aromatic. These three put together is above 80%. And these three have a very poor ignition quality. This is isoparaffin, this is olefin, this is aromatic. They have a lower cetane number, meaning they have a higher octane number. Octane number is a measure of antenna quality. That is what you want for SI engine application. When you look at diesel, its carbon number distribution is from C9 to 23, heavier hydrocarbon. That's why they are categorized as heavy distillate. Primarily, the major contribution is coming from C14 to C18. That is where major contribution is coming from in terms of molecular composition of diesel fuel. Okay, they are heavier hydrocarbon. They have a low boiling range, high boiling range. Okay, they are heavy distillate, high boiling range. Okay, they may not vaporize quickly, but it doesn't matter because in a CI engine, you inject fuel at a high pressure and you are injecting that into high pressure, high temperature air. So external conditions are favorable to vaporize diesel. That's why this high boiling range doesn't matter for CI engine application. But what is more important for CI engine, its ignition quality should be better because it's a self-ignition based combustion mode. So we have discussed how European and US diesel fuel compositions are different. Okay, in different parts of the world based on crude oil reserve, the composition of diesel is going to be different. This is what I wanted to highlight here. European diesel has very low aromatic, only 2%. American diesel has very high aromatic, 32%. Because of this, American diesel has a very low cetane number since it has high aromatic content, which is having poor ignition quality. Cetane number is around 40 for US diesel. For European diesel with less aromatic of 2%, cetane number is very high, around 55. Okay, so you have a significant variation in cetane number because of the difference in the.
Sir?
Yes.
Sir, in this one, Europe, US, we have mentioned now, Gulf also, they are major player in this fuel, no, sir. Why it is not mentioned, sir? It is included with Europe or how it is?
No. I have mentioned here European and US because they have a significantly different composition and property. So the intention here is to highlight how the composition of diesel is different in different parts of the world and what is its effect on the ignition quality. That's why I have chosen these two extreme variations, Europe and US. Our diesel fuel in our country, we primarily import from Gulf, as you said, and they are more or less resembles European diesel, but aromatic is not 2%, it's up to 10% in our country. And we also have a fuel regulation. I will show typical fuel specifications, our Indian fuel specifications. Okay, it is a minimum cetane number is higher than European diesel.
Okay, sir. Thank you.
Okay. So with that understanding, here I am summarizing the major information about the composition, molecular composition, okay, of gasoline and diesel. Gasoline includes hydrocarbons with high volatility defined in terms of distillation temperature. When we discuss the crude oil processing, one of the first step is separating hydrocarbon based on boiling range. Gasoline comes under light distillate category. It has a boiling range of 20 to 200 degrees Celsius. Relatively, it is a low boiling range hydrocarbon compared to diesel. Okay, it is having high volatility. This is one of the important characteristic for SI engine application, because in SI engine, you are introducing fuel during which stroke in the engine cycle?
Suction stroke.
Suction stroke or intake stroke, and you are injecting at low pressure, right? As we have already discussed, 3 to 5 bar, and the temperature is ambient temperature. So the fuel is introduced at low pressure and the temperature is ambient temperature, meaning the fuel has to vaporize by itself. Because of that, you need to have fuel with a low boiling range. Okay, it starts with 20 degree. You can imagine much lower than the surrounding ambient temperature. So this low boiling range hydrocarbon will quickly vaporize, form ignitable mixture. That's why when you discharge electric spark, the engine will get started. Once it reaches warm up stage, it doesn't matter. But you need to have a high volatile or low boiling range hydrocarbon in order to start the engine. Okay, so this is one of the important requirement for SI engine application. That's why gasoline composition includes this high volatility hydrocarbon, meaning that they have a very low boiling range so that they can quickly vaporize. You are not providing sufficient conditions to vaporize the fuel in the engine. The fuel has to do it by itself. The second important requirement, as I said, is its reactivity is low. Reactivity is the ability of the fuel to form radical. Its reactivity is low, meaning that we want fuel with better antenna quality. Otherwise, it leads to knocking combustion. We don't want fuel to self-ignite in a SI engine. It should resist ignition. Okay, resistance to ignition is what is defined in terms of this qualitative term, antenna quality. It is also measured in terms of a property called octane number. So we want fuel with a high octane number. That is the reason why we have more than 80% of isoparaffin, olefin, and aromatic. This three hydrocarbon class put together, it's above 80% because we want to have better antenna quality fuel for spark ignited engine. Okay, so these two are the fundamental fuel quality requirement for SI engine application. That is the reason why refineries process gasoline with such characteristic, okay, high volatility and low reactivity. In fact, the cost of gasoline is more compared to diesel, as you know. Always the cost of gasoline is more compared to diesel. One of the reason is the refinery processes are higher for gasoline to produce gasoline compared to diesel. Diesel refinery processes are less intensive compared to gasoline because we need to maintain or meet these two characteristics. It should be highly volatile, it should have better antenna quality. Because of more refinery process, the cost of refining petrol or gasoline is higher always as compared to diesel. Diesel includes hydrocarbons. You could see that the characteristics are just opposite to gasoline. One, it has a low volatility because it's a heavy distillate, as we have discussed just now. Its carbon number distribution is from C9 to C23, high molecular weight, meaning boiling range is high. It starts from 160. Here it starts from 20 degree. So 160 to 380 degrees Celsius. This is exactly reason this volatility is the ability to vaporize. I already discussed about this. This is the reason why when you go and open your tank, fuel tank, gasoline fuel tank, you could feel the smell of gasoline, right? When you open your motorcycle or your passenger car fuel tank, immediately you could feel the smell of the fuel, right?
Yes, sir.
Because,
Yes, sir. Yes,
yeah,
sir.
the reason is you have a low boiling range hydrocarbon. 20 degrees Celsius is a boiling range, so it will immediately evolves out of your fuel tank when you open it. Okay, that's what you are smelling. In fact, something called evaporative losses, we are going to discuss it later on in the second module. Evaporative losses are the losses that the fuel get lost in the surrounding ambient, dissipate into surrounding ambient when you open the fuel tank for a longer period, right? So that's why we should immediately close the tank. Otherwise, you are losing fuel. Actually, this is what is referred to as evaporative losses. Since the fuel has a low boiling range, it can evaporate and get dissipated into surrounding ambience. In fact, we should not inhale it. I think I already said about this because this benzene ring or aromatic ring based hydrocarbons have the potential to cause cancer. They are called carcinogenic. Okay. So once you inhale, it goes to the lung. Okay. Lung is a unidirectional valve. It goes and get deposit. And it may cause cancer because it is a potential hydrocarbon which leads to lung cancer. Okay, so these hydrocarbons are, from that perspective, it is dangerous for human health. Okay, so we should avoid that. And unfortunately, it has a very low boiling range. And that's why it evolves out immediately as soon as you open the tank. So it is not the case with diesel because it starts with 160 degree. It won't evolve out as quickly. You need to provide a high heat rate. Then only the hydrocarbon will evolve out. Otherwise, it will stays in the tank, fuel tank. Okay. So its volatility is very poor or low compared to gasoline because it's a heavy distillate, heavy hydrocarbon. 160 to 380 is the boiling range. Okay, it doesn't matter for CI engine application, as I said just now, because we are taking care of low volatility by providing better conditions for vaporization. So you are injecting at high pressure and you are injecting into high pressure, high temperature air because you are injecting fuel near the end of compression stroke in the engine cycle. Okay, unlike SI engine where you are introducing during the intake stroke. But the most important requirement is the second one, high reactivity. We just now said that gasoline has low reactivity and diesel has high reactivity, meaning it should have better ignition quality. This is one of the fundamental fuel quality requirement for CI engine application. The ignition is self-ignition. Fuel air mixture has to self-ignite. You are not providing any external aid to ignite. In SI engine, you provide through spark plug. Spark plug, you are discharging high voltage electric spark through spark plug. So you are actually igniting the mixture through this aid, external aid. In CI engine, we don't have any such external aid. The mixture, fuel air mixture has to ignite by itself. From that consideration, the fuel should have a better ignition quality. Otherwise, ignition is not going to happen. Okay, the engine won't even start. So you need to have fuel with better ignition quality measured in terms of property CT number. So you want fuel with a high CT number for CI engine application, high octane number for SI engine application. So this is what our refineries are doing, and this kind of hydrocarbons are included. Gasoline with high volatility and low reactivity, diesel with low volatility and high reactivity. It's just opposite, as you could observe here. So this is all about the composition of this two fuel. Although we use this two fuel in our vehicle, we generally don't pay attention to this molecular composition. But from a combustion perspective, this is very important to know. That's why we spend time to know about the composition of this two fuel. Next, what we are going to discuss here is about the effect of molecular structure on some of the important combustion parameters. So when we do analysis on combustion, we analyze combustion through different parameters. So here I have provided two important parameters. One is ignition delay time and second one is combustion duration. Okay, this ignition delay and combustion duration later on we are going to discuss in detail in chapter 4. Okay, here our focus is to see how the hydrocarbon molecular structure affect the combustion parameters. Okay, that is our focus here. We are not going to discuss in detail about how these parameters are arrived at. Okay, that we are going to do it in chapter 4. Here we are going to see how hydrocarbon molecular structure affect or influence these parameters, combustion parameter. One is delay time, second one is combustion duration. So this parameter, just a quick recap, since we are going to study the effect of molecular structure on these parameters, a quick recap of what these parameters are. One is delay time. I discussed about this in the beginning of this chapter. Is the time elapsed or time duration between start of fuel injection and start of combustion. Once you spray the fuel, it is not going to ignite immediately. It is going to take some time. That time is what is ignition delay time. Okay, it has two elements. One is physical delay
And chemical delay.
The other one is chemical delay. Physical delay is the time required to form ignitable. I use the word ignite, ignitable mixture. Chemical delay is the time required to form radicals. Small t radical is the time required to form radicals from the stable molecular structure. Okay, these two put together is your overall ignition delay time. So there is some time required to form ignitable mixture from the liquid phase fuel after you spray it into the cylinder. There is some time required to form radical from the stable molecular structure of the fuel. That is what is the chemical delay time. And then you have the duration of combustion. How we are controlling load or torque in a diesel engine?
Using a governor.
Okay, no. I am not asking about the device. What is the mechanism? How you are controlling load?
Again, fuel injection.
Yes. Fuel, you are controlling mass of fuel injected in each cycle. Okay. Through that, you are controlling load. In a diesel engine, air is unthrottled. You allow air to the maximum possible extent. You are controlling fuel mass injected per each cycle. In fact, its volume, it gets translated into mass through density difference. We have already discussed about that. Our system meters on volume basis. But the takeaway for you is you are controlling load, which is torque or power from a diesel engine. Torque output or power output from a diesel engine is controlled by varying the quantity of the fuel that is injected into the engine cylinder. Combustion duration is a time duration. There is a finite time required to burn a finite quantity of fuel, which is what you are introducing in each cycle. Okay, so the time taken for burning that fuel is what's the duration of combustion. So these two are important combustion parameter. Later on in chapter 4, we are going to see how we can get these two parameters from measurable data. Okay, but here we are going to look at how the molecular structure of hydrocarbon affect these two important combustion parameters. One is ignition delay, other one is duration of combustion. So now you can see here on the y-axis you have ignition delay given in terms of CAD. What is CAD?
Crank angle, sir.
Yes, CAD is crank angle degrees. Here time, ignition delay is a time elapsed. That's what I said. The time is indicated in the crank angle degree unit, not absolute unit. Can anyone tell me why?
Because RPM is varying, sir. So,
RPM is varying. Good.
so basically, sir, for the same time, suppose if it take the unit time in that way, then, we will not be able to, and we are injecting the oil, fuel in the system by every crank rotation or two of the crank rotation in that way. So it is better to measure in that respect rather than time, because suppose it is equal to 1 second if I take, so the measurement will be different at lower speed and different will be at higher speed in that.
Yes. The most important point you need to take away, I will discuss more about this later on in the chapter 4 when we discuss about combustion analysis. But the point for you to note down is we always analyze combustion in terms of crank angle degree, not in absolute time. Absolute time doesn't make any sense in combustion analysis. We always do it in terms of time is expressed in terms of crank angle degree. That is a degree covered by the crankshaft angular rotation. Because the engine that we deal with, a reciprocating engine, you know that the crankshaft angular position corresponds to a piston position, right? So this linear movement of the piston is related to the rotary movement through the slider crank mechanism. Okay, so you have a piston reciprocating in the cylinder, and so you have a rotary motion undergone by the crankshaft and you have a linear movement undergone by the piston. So through slider crank relation, these two can be related. Okay, meaning at any crankshaft angular position, there is an associated linear position of the piston in the cylinder. These two are interrelated. That's why we always analyze combustion parameters like pressure or any other parameter, combustion derived parameter. In this case, it's a delay time. We always analyze in terms of crankshaft angular position because this crankshaft angular position is related to linear position of the piston in the cylinder. Meaning we are analyzing this combustion parameter with respect to piston position. This is very important information because in an engine operating cycle, we want to know where the piston is located with respect to changes in the working fluid condition. Working fluid here is a mixture of fuel and air. After combustion, it produces products, various product, gaseous product. So we are analyzing this gaseous product or mixture with respect to piston position. That's why we want to analyze any combustion parameter with respect to crankshaft angular duration. Clear? Time in absolute unit doesn't make any sense here because you don't know the information about the piston position when you analyze in terms of time. That's the reason why we want to do it in angular unit, okay, crankshaft angular unit, because this gives me an indirect information about where the piston is located at that point of time. Clear?
Clear, sir.
Yes, sir. Yeah.
So that's why we do this. We always analyze combustion parameters in crank angle, not in absolute time. Okay, so here we have this delay time expressed in crank angle duration at a particular engine running speed, 900 RPM. And x-axis you have cetane number. Okay, cetane number of different hydrocarbon classes which we have discussed earlier. One is normal alkane. Some of the textbooks give this in terms of alkane. Alkane is nothing but it's a normal paraffin. These two are same. Okay, some of the textbooks, this particular hydrocarbon class is referred as alkane. Alkane or paraffin are synonym. They convey the same thing. So you have a triangle without fill-in is normal paraffin, and then triangle with fill-in, which is olefin, then circle without fill-in, cycloparaffin, then circle with filled-in aromatic, then isoparaffin. This is diesel fuel, this is jet fuel. We can ignore this. So this is a real diesel fuel, and these are the hydrocarbon classes, major hydrocarbon classes, which we have already discussed. Okay, so for these different hydrocarbon classes, we have provided cetane number in x-axis. In the y-axis, we have provided ignition delay time. Now, if you look at normal alkane, triangle without fill-in, it is coming here. It is having very high cetane number. We already discussed about this. This normal alkane or normal paraffin is having a high cetane number because of better ignition quality. Physical meaning is it can readily form radicals. So it has a high cetane number. On the other hand, if you look at the other extreme, circle with filled in is an aromatic class. It is having very low cetane number, meaning the delay time, ignition delay time is too long. In between, you have other hydrocarbon classes coming in. Okay, so the important information from this plot is this ignition delay time varies with cetane number in an inverse manner, meaning if you have a high cetane number, the ignition delay time is reducing, right? This is expected because high cetane number means better ignition quality. So delay time drops with the cetane number increase. This is one of the important information, and this is true for any hydrocarbon class that we have considered here. As long as the cetane number is high, the ignition delay time drops. This is the reason why cetane number is considered as a measure of ignition quality of the fuel. Higher the cetane number, lower the delay time. This is one of the important information. Second important information is you could see that the trend is non-linear trend between ignition delay and cetane number. The other important information is you could see what is happening after cetane number 40. This is something like a threshold cetane number value. When the cetane number drops below 40, what is happening to ignition delay time?
It is increasing sharply, actually.
It increases sharply. You could see the sensitivity here. Until above 40, you could see there is almost flat, meaning that the slope is less. But here the slope is higher. Higher slope indicates that the sensitivity is more, right? When the cetane number falls below 40, there is a sharp increase in the ignition delay time. So what will happen in a real engine? There is a sudden increase in the delay time. How it affects CI engine combustion? How it affects the engine? The sharp increase in ignition delay.
That means we have to
rate
inject.
of pressure rise will be more for each crank angle.
Rate of pressure rise is going to shoot up. Okay, eventually it may lead to knocking combustion. Eventually it may lead to engine damage. It can damage the engine. The immediate thing you can feel when you drive the vehicle with such a poor ignition quality fuel is you can feel the vibration, right? When combustion noise is more, it will translate into vibration because noise is due to, as you rightly said, high pressurized rate. So pressure waves propagate at a higher velocity and strikes the component, engine component. So it will set the component to vibrate. That vibration you can feel, although we suppress vibration to some extent. We provide some cushioning effect when you design the engine, but nevertheless, if the combustion noise is high, it will overcome all this. And when you drive the vehicle, you can feel that when the engine is knocking. Okay, so you could feel the vibration. The worst case scenario is engine will get damaged. So the point for you is we should not use fuel with cetane number less than 40. Otherwise, you will have a problem of very long ignition delay that will translate to high combustion noise, vibration. Final worst case scenario is engine damage. Okay, so for all the hydrocarbon classes, there is a significant effect on the cetane number, and thereby it affects this important combustion parameter, ignition delay time. Okay, and thereby you may have either a smoother engine operation or a noisy engine operation, depending on the ignition quality of the fuel defined in terms of cetane number. That's why we always keep a check on cetane number when we do fuel. When you fix the fuel quality standard, this is one of the important specifications. We need to use fuel with certain minimum cetane number. In India, it is well above 40. Yesterday, I said that European diesel has a high cetane like Indian diesel, but American diesel has a cetane number of 40. 40 is a threshold value. Suppose if you use fuel with cetane less than 40, you could see what effect it will have on the engine. Okay, it can even damage the engine. So this is based on the first plot. It is an important information you get that the hydrocarbon molecular structure based on what kind of hydrocarbon present in diesel, it's going to affect the delay time in an actual combustion phenomenon. Next, you look at this plot number 4. What you have here is ignition delay time in x-axis, combustion duration in y-axis. Just now I said what is this duration of combustion, which is the time taken to burn a finite volume of fuel in the engine, in a diesel engine. Now, this relationship between ignition delay and combustion duration is captured for this different hydrocarbon classes as well as diesel fuel. So when they do the plot, so here you have ignition delay time information. When you plot this delay time with combustion duration, you could get a trend like this. What kind of trend is this?
It's a linear trend with
Linear trend.
Right.
You have a linear trend. What I can infer from this plot is when the ignition delay increases, the duration of combustion is decreasing. This is what I infer, and it's almost like a linear, right? Unlike ignition delay, which is non-linear, here it's almost like a linear trend. Now, if you use hydrocarbon with more aromatic circle with filled in, it is coming here, and this is a triangle without filling, which is normal paraffin. So normal paraffin is having shorter ignition delay. That is what we observe from plot 1. So the duration of combustion is higher in that case. But aromatics are going to have a longer ignition delay. But in that case, the duration of combustion is shortest, as you could see here. So can anyone tell me why the duration of combustion is shortest with hydrocarbons like aromatic, which is having a longer delay time, whereas it is longest with hydrocarbons like normal paraffin, which is having a shorter delay?
So basically, if we go for a longer paraffin, that means once the that means octane number is very high in that way compared to
octane number is high, cetane number is low, very low.
So what happens, sir? Once the flame is initiated by first this thing, what I meant to say is initiation of first flame. After that, the fuel will burn very fast in that way because it will behave like a more of SI engine fuel in that way.
Exactly.
So once the flame is generated, that will burn very fast because octane number is very high.
Exactly. So what is happening is a little bit of understanding of combustion stages is required. I will talk more about it later on in this 3rd chapter. But here, just take a note that in a CI engine, combustion, okay, you have a delay time followed by premix phase combustion. These are the different stages of combustion in a CI engine, followed by diffusion phase combustion. So you have a delay time, that is what we have discussed just now, followed by premix phase combustion, followed by diffusion phase combustion. And we know that we are injecting a fixed quantity of fuel into engine cylinder to achieve a given load. So the fuel quantity that you inject is fixed. So this is constant. Okay, and you have these different stages of combustion. Now, for a fixed or constant value of fuel, when the delay time is more, what will happen to premix phase? Premix phase follows ignition delay time. Premix phase is almost like a constant volume combustion, instantaneous combustion, because whatever fuel and air premixed during the ignition delay burn instantaneously. That's why I say that it's almost like a constant volume combustion. The burning is almost instantaneous in premix, because during delay, you already pre-mixed this fuel and air within an ignitable proportion. Once ignition happens, self-ignition happens, it burns instantaneously in pre-mix phase. It's almost like a constant volume combustion. Then you have something called a diffusion phase combustion. Diffusion phase combustion is generally approximated as constant pressure combustion because it's a slow burn phase. You can control this diffusion phase by controlling the injected fuel quantity during this period of time. So this is like more of a controlled combustion. This is like more of an uncontrolled combustion. This is what is happening after the delay time in a CI engine. This is how the combustion event happens in a diesel engine. You have a delay, ignition delay, premix phase, diffusion phase. Now what we are looking at is, what we are seeing here is when the delay is more, the duration of combustion is dropping primarily because now you can say what is happening here. When delay is more, what is happening?
Premix combustion is more.
You have more intense premix. and you have less intense diffusion because you have a constant volume of fuel introduced, right? Most of the fuel get burned during premix, which is almost like a constant volume combustion. And less fuel burns in diffusion combustion, which is a slow burn phase. It's just opposite to premix phase. Slow burn. Okay, burning will take place very slowly. Okay, here it is instantaneous, here it is very slow. Now, when the delay time is longer, if you have a very long ignition delay time, this is going to be intense, more intense, instantaneous combustion. This is less intense, meaning that the slow burn phase is less, premix phase is more. So you have overall combustion duration reduced considerably. This is what you are seeing here. Overall duration of combustion reduce considerably when the delay time is longer because you have a more premix, less diffusion. Opposite is true with low or shorter delay. When delay is shorter, you have less premix phase, which is instantaneous combustion, and more diffusion phase. When diffusion phase is more, the duration of combustion is going to be higher because it's a slow burn phase. Did you get what I'm saying?
Yes, sir. Yes, sir.
So in terms of thermodynamic cycles, you may be familiar with this thermodynamic cycle. We always approximate SI engine combustion through Otto cycle because the heat addition is constant volume heat addition. That is process 2-3. This is a heat addition process. In a real engine, it's a combustion process. We approximate heat addition in a SI engine as constant volume, whereas in a diesel engine, we either approximate it as constant pressure or more suitable approximation is dual cycle, wherein partly it is constant volume, which is what is premix phase, partly it is constant pressure, which is what is diffusion phase combustion. This is more better approximation, right? Closer approximation compared to the diesel, which is having only constant pressure heat addition. You are missing out premix phase here. Okay, so this is more suitable for CI. And this is approximation we give for SI when you do a thermodynamic analysis of IC engine, okay, using these cycles. So we don't want instantaneous combustion. We don't want this shorter combustion duration for diesel engine. So when you have a shorter combustion, when you have a shorter combustion duration with more instantaneous heat release, the duration is shorter. The advantage is shorter. Can anyone tell me what advantage you will get if the combustion is almost instantaneous with the constant volume?
Would like massive pressure on the piston, sir. So
no advantage. What benefit you get?
So time taken is reduced.
Time taken is reduced. Time taken.
Higher work output.
Sir, better burning, sir.
Better efficiency.
Better burning.
Yes,
Time
yes,
for
yes,
time required to burn is very less. Better burning. So you will see that it results in high thermal efficiency.
Yes.
Right, which will reflect in terms of mileage. So as an end user, we are more focused on mileage rather than thermal efficiency and all. But for analysis, thermal efficiency is an important parameter. So when the combustion is instantaneous, you have a lot of energy release happening. So you can recover it through work. And the time available for heat loss is considerably less. This less heat loss will increase thermal efficiency reflected in better fuel economy in a vehicle. Okay, because of this. This is preferable from this perspective, but we don't want this to happen in a diesel engine. We don't want instantaneous combustion. In fact, we want to reduce the premix phase and increase the diffusion phase in a diesel engine. Can anyone tell me why? Although you have an advantage of thermal efficiency, we don't want that to happen in a diesel engine.
durability, sir. Durability of the engine.
Durability, exactly. So the life or durability of the vehicle will get reduced. The engine will get damaged. If you undergo complete premix combustion, the major problem, worst case scenario, is the engine will damage. Second one, safety concern. Third one, the engine will provide discomfort. There will be discomfort when you drive the vehicle. That's what I said, right? So you will have vibration, noise and vibration from the engine, right? It's a discomfort. So you know about NVH characteristic, we want to maintain, right? Better NVH characteristic, which is very important for a vehicle. It will be poor, right? But worst case scenario is even the engine will get damaged. So we don't want this instantaneous combustion or more premix combustion. That's why we approximate diesel as a constant pressure or progressive combustion. We want a progressive combustion from this aspect. That's why we don't want to have more of aromatic kind of hydrocarbon classes in diesel, okay, which eventually leads to very high ignition delay, very short combustion duration, but the durability or life will be reduced and the engine will get damaged and combustion noise will be high, which we don't want. Okay, we prefer to have only normal alkane, which is normal paraffin kind of hydrocarbon. Although we have a longer combustion duration, we prefer to have that because the combustion will be progressive, the durability will be high, the engine will run smoothly. This is what we want. Okay, so from this two plot, we understood that the hydrocarbon type of hydrocarbon that you include in the molecular composition of diesel has a significant effect on these two combustion parameter. One is the delay time, and the delay time will also affect the duration of combustion. Okay, you have another two plots shown here, this one and this one. Let us look at this plot. In this plot, what is provided is you have ignition delay on y-axis. What do you have on the x-axis? Carbon chain length. So we are changing the carbon chain length. The number of carbon atom is changing from 5, 10, 15, and 20. That is what you have on x-axis. You have analyzed how the chain length, carbon chain length, affect ignition delay time for these three hydrocarbon classes. One is normal paraffin, other one is alkene is olefin class. This is cycloparaffin class. This is cycloparaffin. This is olefin. This is cycloparaffin class. And this is paraffin class. So what I am talking here, I am changing the carbon chain length. So we have already discussed about this hydrocarbon structure. So if you take a normal paraffin, you will have any number of hydrocarbon. This is one of the hydrocarbon, normal octane. Likewise, you can have any number of hydrocarbon coming under this class. All will have same chain-like structure. But what is going to be different? Length of the chain. So you can either increase the length or decrease the length, shorten the length by varying the number of carbon atom. Did you get what I am saying?
Sorry, sir. Once more, please. I'm sorry.
So in a normal paraffin class, you will have n number of hydrocarbon. Number of hydrocarbon present in normal paraffin class can be higher. All the hydrocarbon will have a chain-like structure. But what you can vary, what is different in this different hydrocarbon is the length of the chain.
Right, sir.
Length of the chain means the number of carbon atom. This is what I have shown in the plot. The number of carbon atom will decide the chain length. Okay, if you have less number of carbon atom, the chain length is shorter. If you have more number of carbon atom, the chain length is longer. Did you get? Similarly, for olefin, this length is going to be different based on the number of carbon atom. This can be higher or lower. So the length is going to be different in different hydrocarbon present in this particular class. But all will have a same molecular structure. Only length is changing. Similarly, in a cycloparaffin class, the base structure will be ring, as you could see here. This ring structure will be maintained. When I say that I am increasing chain length, what I am doing is I am increasing the side chain. Okay, so here I have one carbon atom, or I can have two carbon atom, or I can have three carbon atom, and so on. This is what I mean by I am varying the chain length for cycloparaffin class. Did you get?
Yes, sir.
Now, what will happen when I change the chain length in terms of number of carbon atom? What will happen to the ignition quality? Will it increase or decrease? Suppose I am increasing the chain length. Here also I am increasing chain length. When I increase chain length, what will happen to ignition quality?
So I think the bond will become bigger, so the C10 will increase further.
C10 number will increase. Ignition quality will improve, right? Can I say that?
Yes, sir. Because bond strength is reducing.
What is happening when I increase chain length? The number of carbon atoms are increasing. Number of hydrogen atoms are increasing. When I increase chain length, it means the radical formation tendency is going to increase. If you have a shorter chain length, you have less number of carbon atom, less number of hydrogen atom. Radicals are formed from carbon and hydrogen, right? So when you have a longer chain, you have more carbon, more hydrogen atoms. Meaning, with the given activation energy you provide to initiate combustion, the radical formation tendency will be increased. In other words, ignition quality will be improved. This is what you are seeing here in this plot. As the carbon chain length increases, the delay time is decreasing for all the three classes. Ignition delay time is decreasing because ignition quality is improving. This is one information, and that is true for all the three classes. But you could see the slopes are different. Here you have a steeper slope, higher value. Here also somewhat higher. Here it is almost flat, less slope. What is the meaning of this? The sensitivity in these three different classes to change in chain length is different. The sensitivity in the sense, the way the ignition delay varies with carbon chain length increase is different in these three classes. For cycloparaffin, it is steeper, meaning it shows very high sensitivity, meaning if I attach a side chain, the radical formation tendency is increasing. The base structure is a ring, which is very stable structure. It is very difficult to form radical. But by increasing side chain length, I am increasing the radical formation tendency. That's why ignition delay time drops sharply for cycloparaffin class, which is almost flat in normal paraffin, because normal paraffin already has a better ignition radical formation tendency. So by increasing chain length, the change in delay time is not much, whereas it is significantly high for cycloparaffin class because the base structure is very stable. Same thing you could observe here in the third plot. What you have is ignition delay time. Here you have normal paraffin, olefin, cycloparaffin. You have ignition delay expressed in terms of chemical delay time, T with the subscript CHEM, that is chemical delay time. T with the subscript PHYS, this is physical delay time. Okay, so this is physical delay time. This is chemical delay time. This is compared for these three classes. One is normal paraffin, this is olefin, this is cycloparaffin. So what you could observe here is for normal paraffin and olefin, chemical delay time and physical delay time are almost same. Whereas for a cycloparaffin class, this one, chemical delay time is significantly high compared to the physical delay time. I already told you that in a CA engine, most of the time, physical delay time is considerably less compared to chemical delay time. The time required to form radical is more compared to time required to form ignitable mixture. That is what is a physical delay time. Right? In diesel engine, you have favorable conditions, external conditions to form ignitable mixture quickly, but chemical delay time is controlled only by molecular composition, that is hydrocarbon structure. When you have a cycloparaffin kind of structure, you are going to have a long ignition delay, primarily because the chemical time, which is the time required to form radical, is considerably high compared to physical delay time. So overall delay time is influenced more by chemical delay time as compared to physical delay time when you have hydrocarbons like cycloparaffin. Okay, so this kind of hydrocarbon will have considerably longer chemical delay time, thereby overall ignition delay time is also longer. Okay, so it's time up. I stop here. If you have any questions, you can ask.
So it was very enjoyable to learn all those things. Thank you, sir.
Thank you. Do you have any doubt?
Yes, sir. One question, sir.
Yeah.
Sir, can we go back to the slide, please?
Yeah.
Yes, sir. So here in two hexane and one hexane, like alkane and this paraffin. So we have longer physical delay time. So is that because of the molecular weight of the fuel?
Okay, this time you are talking.
Yes, yes.
So this time, physical delay time is primarily the time required to form ignitable mixture, right? So what is happening during physical delay, we already discussed in the beginning of the course. That was the first topic we discussed. Once you spray, once you inject the liquid phase PA, it has to mix with air within an ignitable proportion. That time required is what is physical delay time. When the fuel have poor spray characteristic, but the fuel has very poor volatility, it is going to take longer physical delay time.
Yes. So because of the longer chains, the volatility of the fuel decreases.
No, the chain length affect radical formation. Okay. Physical delay time is influenced more by boiling range, thermophysical properties, and spray characteristics.
Okay, sir. Thank you.
Chemical delay time is influenced more by the molecular composition and structure. Whether you have a chain-like structure or ring-like structure, that is going to affect only this time, chemical delay time, not this one. This one is affected by boiling range, thermophysical property, spray characteristic. So you are introducing liquid phase fuel. Combustion is gas phase. So you need to get into gas phase quickly. So there is associated thermophysical property that influence how quickly liquid phase fuel get into gas phase fuel. And then after you get into gas phase, you have to mix within the ignitable range. You have to mix with air, right? Fuel has to mix with air within ignitable range. All this are happening during this period.
Yes. So, sir, actually, the thermophysical property will also ultimately vary because of the chemical properties only, sir. So, means that's what I understand.
No.
Like, I just want to
physical property and chemical properties we can separate. Chemical property or chemical delay time is primarily based on the kinetics, chemical kinetics, and kinetics are different based on this whatever we have discussed here. Kinetics are different based on this molecular structure. Okay. But physical properties are different. Physical property, there are a large number of properties like density, viscosity, thermal conductivity, boiling range. All these are physical properties. Clear?
Understood. Thank you, sir.
Fine. Thank you. Anything else?
Sir, this data what we have just seen, is it individually evaluated for the each and every molecule structure, or it's a mixture?
No, this whatever I have shown is for individual hydrocarbon. Individual hydrocarbon, but diesel is a mixture. Diesel is a mixture of all. Now, to understand the effect of these individual hydrocarbon, they are evaluated individual. And then we are analyzing a mixture of hydrocarbon, which is what is the actual diesel fuel.
Okay.
Fine.
Sir, am I audible?
Yes.
Sir, just one query on the pre-mix phase and diffuse phase. Can you just summarize that comparison between what happens if it is a paraffin and versus a aromatic? Can you just summarize the comparison alone?
Pre-mix phase and diffusion phase is here. So you have a delay time, ignition delay time, followed by premix phase, then followed by diffusion phase. That is how CI engine combustion takes place. Suppose if you have more aromatic, okay, what will happen to the ignition delay?
Delay will be more.
Delay will be more. Then what will happen to premix phase? You have a long delay.
Yes. Premix should be faster or? Yeah.
More intense. I use the word more intense because you have a longer delay, more fuel is injected during delay. That is what is going to burn in the premix phase. So this is going to be more intense because I have a long delay with aromatics, which is having poor ignition quality. Now, since you have a constant fixed volume of fuel that you introduce in each cycle, most of the fuel is introduced during delay time, burns instantaneously. So it means there is less fuel that burns in the diffusion phase. So what will happen to the intensity of diffusion phase? It comes down for a finite volume of fuel, right?
Yes.
So with more aromatics, you have a longer delay, more intense premix, less diffusion. This is a slow burn phase. This is instantaneous phase. So when you have more intense premix phase, the overall combustion duration is going to come down. This is what I said. When ignition delay is more, combustion duration will come down. This is the case with aromatics.
Clear, sir.
Opposite is true with our normal paraffin. Normal paraffin has a better ignition quality, shorter delay, less intense premix, more intense diffusion. So combustion duration will increase because this is a slow burn phase.
So now coming to that radical formation with respect to aromatics. So in aromatics, radical formation would be easier or it will be difficult?
Difficult.
Difficult.
Radical formation, if it is easier, the ignition will happen quickly.
Correct. Okay. Got it, yeah.
Okay.
Thank you, sir. Yeah.
So fine. So I'll stop here. It's time up. I'll see you tomorrow at 6 o'clock. Thank you.
Thank you, sir.
Thank you.
Thanks a lot, sir.
Thank you.